Okay, now when we are talking about sensor sizes, I want to give you an idea of the difference in the size. So I can throw out numbers at you all day and say, okay, well, take a look at this 2/3 sensor. It's only 8.8 millimeters by 6.6 millimeters versus a 35 millimeter camera, which is something like 36 millimeters by 24. And that doesn't give you a good idea of the actual difference in size. Well, to scale, I've painstakingly drawn out two rectangles that show you approximately how much larger a digital SLR format sensor is compared to that of a compact camera. So on the left, we have a compact sensor from a format called 1 divided by 2.5 inches. It's kind of small. Then on the right, we have an APS-C sensor. So it's not a full-frame sensor still. It's not actually 35 millimeters, but it's a little bit smaller than that. And this is something that you would typically find in low to mid-range digital SLRs. So the very, very expensive, $8,000 digital cameras will generally have full-frame ones. But the ones that are more accessible to all of us are more likely to be this size. Then this shows you the difference in size between these two formats. And you may know that one of the aspects of this course is that you don't have to have a digital SLR to complete all of the assignments. In fact, you can use the Panasonic camera that's available from the Church Street Lab to be able to take the photos and complete the assignments. But just to show you that even we here at the Extension School are on a budget, we were not able to get cameras that have something that has a sensor that is that big. In fact, the sensor in the Panasonic Lumix is this exact sensor. It's a 1 divided by 2.5 inch camera. So if you are using that camera, you are using a compact digital camera that has features that mimic that of a digital SLR. Okay, but one of the things that I really want to get down to here is actually talking about the difference of these sensors. So here, I've given them both a megapixel count. They're each 6 megapixels in size. So this means that if they have an aspect ratio of 3:2, then each one is going to have 3,000 pixels across by 2,000 pixels down. If you multiply those two out, you get 6 million pixels, and that's why I chose 6 megapixels. It's very easy to remember 3,000 by 2,000. So we have 3,000 pixels across on this one, 2,000 pixels down, and again the same thing here, 3,000 pixels across and 2,000 pixels down. And if you actually do the math, if you take the width of each of these, divide it by 2,000, you can figure out exactly how large each pixel is on this sensor. So we do the math, and I've already done it for you. On the left side, we take 0.007 meters divided by 3,000, and we actually get 2.3 microns, which is 0.0000023 meters. So it's very, very, very small. And just to give you an idea, the width of a typical human hair is about 100 microns. So 1/50th the width of the human hair is 1 pixel in this tiny little LCD. Very, very small. We're talking really small, very microscopic sizes here. Now, even though this one is much bigger, it's not a lot better. It is considerably better, but it's not a lot better. If we take the width here, divide it again by 3,000 because they have the same resolution, so we're going to expect the pixels to be larger. But this one on the right is now 8 microns. So whereas the pixel on the left is only 2.3 microns, the one on the right, the pixel on the right, is now 8 microns large. Now, if you figure out the area of each of these pixels, now remember that one of the very important things about photography is, for example, the area of the lens. That the size of the lens that's allowing the light to enter into the camera. If you double the area, you're letting in twice as many photons, which means you're getting more light, which is generally a good thing, right? Because then your camera doesn't have to work as hard to try to generate an image from that particular lens. So if we figure out the area of 1 pixel on each of these, so it's just a tiny little fraction of each of these, then we find out that the area of 1 pixel on the left is 4 microns versus the area of a pixel on the right is 64 microns. So this is 16 times larger, or if you multiply it by 2, so 4 times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, we get 4 stops more light in this sensor on the right. Just by having a larger sensor with the same number of megapixels, we get 4 times more light that's available to us to do whatever the hell we want with. So this means that we could do a couple of things. What could we do with this extra light? So let's talk about maybe ISO, for example. Maybe our sensitivity. Yep.
Well, you wouldn't have to use as high an ISO because you get more light and you have a larger f-stop.
Right. So even though the camera manufacturers sort of normalize all of this so that ISO 100 on one digital camera that's this size is approximately equal to ISO 100 on a camera of this size, you can imagine that because ISO 100 on this camera is already getting so much more light, 16 times more light, 4 stops more light of information than this one, that it's just going to be cleaner. There's going to be more signal and less noise. And this is exactly what happens. Now, there are other factors involved here. When I'm talking about sensor size, I'm assuming that technology hasn't advanced at all for either sensor. So we're assuming that this is the same sensor technology developed side by side at the same amount of time. Newer sensors perform better. So with time, the compact cameras have gotten better for the quantity of megapixels that they have, so that they're a little bit less noisy. They have better signal to noise, variety of other things. And so what I'm talking about is keeping all other things except the size of the sensor itself constant. Because as technology progresses, it sort of throws a wrench into all of this, and we have to try to figure out again what all of this means, or what all of this does. Okay, so you're starting to see, hopefully, what the difference in sensor size can do to the quality of our images. But there's something else that it impacts as well, and that deals with the actual light itself. So the actual optical properties of the lens, or rather, that is probably not accurate to say, but the actual image that it captures, if we're using the same lens, for example, is different. So imagine for a moment that I just have a lens. I don't care what the focal length is, I don't care what the aperture is, anything like that. Just pretend you have one lens and you put it in position over this sensor right here. Then you take a photo using that lens with that sensor, okay? You have a particular photo. Let's say it is of this room, for example. Now, let's say you move that same lens over to this sensor right here on the left and take another photo of the same location, the same lighting, everything is the same except the sensor. You've just changed the sensor. How, excuse me, I'm sorry. How does the image actually look different? So not brighter, so it's the same amount of light. So what about the image itself?
It's going to be less defined.
So less defined, so that is a possibility. It depends on the optical properties of the lens. But imagine that we have a lens and it's projecting an image onto this square, or onto that rectangle right there. Then we move it over, it's projecting the same image over here, but we're only capturing a smaller portion of it. So that means that we are essentially cropping the center of that image for this smaller sensor right here. Okay, does that make sense? So that now, rather than being a picture of the entire room, for example, we put this lens in front of the smaller sensor, we get a much narrower field of view. Maybe only the center few chairs, for example, or maybe just the door in the back, as an example. And that is exactly what happens. And so you might remember this particular image from when I was talking about perspective back in the optics lecture. But we can reuse this image when we're talking about the difference in sensor sizes. Okay, so let's imagine, so just to give you a quick reminder of what these images were showing you, we had 4 images here. What we were trying to show was the difference in perspective when we moved the camera closer or farther away from some set of objects. So in the first picture, we took an image on a camera at 35 millimeters. And so again, you can imagine that this is like taking a picture with that large sensor with some particular image. Then we cropped the center part using this, that little red box. We cropped the center out, blew it up a little bit, and looked at how that looked like, and that is right here. Then we removed that lens, this original lens that we used to get this particular shot. Number one, we put a longer lens on it, which means it's more zoomed in, more telephoto. We took the photo again, we got this third image right here. And recall that this third image and the second image are essentially identical. Well, except for the resolution, because you've lost resolution by cropping some of it out. But how it looks, the field of view, the perspective of the two hasn't changed. So it looks exactly the same. Okay, so if you think about how we can reapply the same image, this same thing applies to smaller sensors as well. Excuse me, I'm sorry. Okay, so let's say that image number one we took with that particular lens in front of this large sensor right here. Then we looked at the image on our computer screen, and number one is the image that we got. Okay, now let's say that we moved over that lens from this large sensor, put it in front of this smaller sensor, and took another photo. It is as if we've cropped out this red portion of the image again, and we're looking at this. So it's essentially the same thing. Does that make sense? So what we are saying is that, okay, well, using this lens, this 33 millimeter lens on this small sensor is as if we are using a much longer lens on this larger sensor. Everybody with me so far? Okay, so a shorter lens on a smaller sensor is more zoomed in versus a larger lens, versus that same small lens. When I say small, I mean short lens. Same short lens on a larger sensor is more zoomed out. And so this brings up this notion, this idea of something called the field of view crop, or a crop factor, or you might hear a variety of different things that are out on the internet lately. And that is discussing the actual difference of using one of these cropped sensors, so one of these APS-C digital SLR sensors, for example, that have a smaller sensor than a full-frame digital SLR sensor. They're talking about the difference in the field of view from one sensor to another. And this has a variety of implications to us. So one of them is that if we are using a crop factor camera or a digital SLR that has a smaller sensor than full frame, then it alters how our images will look. And more specifically, it's cropping out the center of those particular images. Now, there's a lot of arguments to be said about this particular notion of photography, and it's hard for me to address all of them, but realize that this really only becomes true when the megapixels, or the quantity of pixels, is the same in each sensor, and I'll explain that in a second. Yes?
I realize I actually am kind of confused.
Okay.
Why is it that using the smaller sensor is like putting on a different lens rather than like having cropped a photo? I think that's where I got lost.
Oh, okay. Yes. So it is all right. So it is correct to say that it is as if it is cropping the photo. So when you move that lens,
Going from 1 to 2, not from 1 to 3.
No, not exactly, because in this precise example here, if we had 6 megapixels in this first image, for example, when we actually cropped out in software that red box, then we had a much smaller number of pixels in this image right here. right? But what we are talking about is using a smaller sensor that has more pixels, so it's denser. So that means that now when we move this lens to a smaller sensor, this red box, rather than having less resolution, now has the same resolution as the original photo, but has the field of view of the original cropped photo, if that makes sense.
Okay, yeah, I get it now.
Okay, so it's an important distinction to say that when we are using one lens that's designed for a larger sensor, when we're using that same lens on a smaller sensor, it's not as though, so even though it alters the field of view so that it's as if we are using a longer lens, we are not using a longer lens. We are still using however many millimeters of focal length that is. It's just that we happen to crop out the center of that image circle. And that is what I'm trying to show with this image here. So lenses, as you know, are circular. And when light passes through them, it passes the image through in a circular fashion. So the image circle, as it's called, of the lens looks like this big circle. Now, if I have a full frame camera, or I'm using a film camera that has a legitimate 35 millimeter frame, I use as much of that image circle as I possibly can when I'm taking the image. So using this red box, for example, I'm taking that photo with a full frame digital camera, and the image that you see within this red box is the resulting image in the full frame digital camera. Now let's say that I move that same lens onto a crop camera, onto an APS-C camera that's going to be a little bit smaller than the full frame camera. What I see then from this entire image circle, I'm wasting all of this extra information provided to me from this lens, but I'm getting this center part cropped out of the image. And if these two cameras have the same resolution, then it is as if I have zoomed in a little bit more for free with this lens. Of course, it's not quite for free because, as we know, the same resolution means that the pixels are smaller, so it's a little bit noisier than a much larger sensor that's going to have cleaner pixels, but is going to be more zoomed out. So as you can see, there's, as with most things photography, a lot of give and take here. So if we have, for example, a wide angle lens, we're trying to take a photo of the entire room, for example, we generally want that wide angle lens on the full frame camera because then we get as much of the room as that lens will allow me to have as possible in the photo. So using a cropped camera, we're getting rid of some of the wide angleness, so to speak, of that particular lens. So we can battle with this. So how, let's say that I put a wide angle lens on a full frame digital camera and I'm able to capture this entire room in that photo. Now I move that same lens over to a cropped camera. I take a photo again. It's going to give me less of the room, right? So how can I battle with that? How can I get, not with that same lens of course, but how can I get all of the room into this camera that has a smaller sensor? Yep, so we need a wider angle lens. So this means that for this smaller sensor, we have to design a new lens that has a shorter focal length, which allows me now to match the width or the field of view from that original combination in this smaller camera. And so just to give you another, just to hammer this point home even more, I know there's a lot of like boxes and lines and stuff, but if you work through this image, it's not all that complicated. So let's say that we put a 50 millimeter lens, for example, on two cameras. First, a full frame camera, this red box, then an APS-C camera or a cropped camera, which is the blue box. Now, when you actually look at those photos on the computer, you see this very top image from the full frame camera, and you see this image from the cropped camera. So remember, when you're viewing these photos on your computer, you generally view them at about the same size, right? So maybe full screen, for example. So when you blow up this image to be the size of your screen, then it's going to look more zoomed in as the full frame one. So this is the same thing that we've been talking about, just another way of demonstrating this same idea. Now, however, let's say that we try to adjust for the fact that we're using a long focal length or a medium focal length lens on a smaller sensor by using a longer lens on a larger sensor. We can see that now with the 70mm lens, it's going to be slightly more zoomed in, and the end result is a photo that looks approximately the same as that shorter lens on the smaller sensor. Okay? Hopefully that makes sense. Now, this is something that's very important, and this is a very heated debate on the internet. Once you start looking into some of the more expensive cameras, when you're trying to decide between a cropped sensor camera, such as an Nikon DX or an APS-C from Canon, versus a full-frame camera, which is available again from both, and there are other manufacturers as well that offer these, you will very frequently see this become a religious debate online about how, oh, full frame, that's the way to go. If you don't have that, you're an amateur, you don't know what you're doing, so on and so on and so forth. And that's not necessarily true, I don't think. It's different strokes for different folks, if you'll let me coin a very cliched phrase. And the whole reason that a cropped sensor might be better, if it has a higher resolution, then you might be able to get the equivalent of a longer lens for cheaper. So if, for example, you do a lot of sports or bird photography, for example, or airplanes or something where you need a lot of reach, then maybe you want a slightly smaller sensor for that reason. Now, it's not really all that useful if you have a small sensor and not as much resolution as the full-frame sensor, because then you might as well purchase the full-frame sensor and use that resolution, just crop out the center, because that's the same thing anyway, right? So if you have, let's say, a 12 megapixel sensor here and only like a 4 megapixel sensor here, for example, just to show an extreme, then you're not going to get more resolution out of this smaller sensor, so you're not going to get as much reach. It's not going to be as if you are zooming in as much. You're just losing this image circle, and you lose the advantage, well, the supposed advantage of this cropped sensor. Now, there's another way to look at this as well. Using a high-resolution full-frame sensor, you have the most options. You could use the widest angle lenses that are available. You can crop when you need to and get that reach. You get the most quality out of it that's available at that particular time. So it's really, I mean, as I always say with regards to digital photography, you have to decide which way is best for you. And I think, at least for now, many of us will still be choosing the crop sensor only, if nothing else, but for cost, because we can still get these crop sensors for considerably cheaper than we can these much larger sensors. Okay, now if this applies to pretty much every type of camera that's available on the market today. So this is a front photo of the Panasonic Lumix that's available again from the Church Street Lab, and I'm using this only as an example because some of you may have used this camera, may be familiar with how it behaves or how it operates. And you'll notice that on the front, and this is something that we went over in the optics lecture, there's a variety of information available. So not only is it the f-stop range, or the f-number range that's available on that lens, we also get to see the focal length itself. So on this lens, for example, we see that we get a focal length of 6 millimeters, and I know it's upside down, so you have to turn your heads over, from 6 millimeters at the widest end all the way to 72 millimeters at the most telephoto end. Now, generally what we see online is a conversion from these small focal lengths, because keep in mind this is the actual focal length of the lens. It's actually a 6 millimeter to 72 millimeter lens, but because the sensor on this camera is so small, it's as if this is a much longer lens on a 35 millimeter camera. And generally we try to normalize this information by converting it back to a 35 millimeter equivalent. And frequently you will see that in reviews or in specifications, you will see something that says the actual focal length is shown here. Then they do a conversion and show you and tell you what it would be if you were using similar focal lengths on a 35 millimeter camera. And this is useful for us because then we can start to get an idea of how wide or how telephoto something is just by knowing this equivalency. So we don't have to, we don't actually have to guess how wide 6 millimeters is. And there's actually a way that we can multiply it out. And so in this case, this particular lens operates in the 35 millimeter equivalent from 36 millimeters, which is sort of wide, but not really, all the way to 432 millimeters. And if you're familiar with digital SLRs or 35 millimeter cameras, then you will know that buying a 400 millimeter lens is not only big, but it will probably be the only purchase you make that year because it is so expensive, it is so heavy, you're going to have chronic back problems trying to carry it around. It's going to be a big hassle. So we can simulate having a very, very long lens by using one of these smaller sensors and using a shorter lens as well. Now, how did we calculate this, this particular figure from this? Well, you have to know how many times smaller that particular sensor is compared to 35 millimeters. So when we are talking about, for example, an APS-C sensor or a DX sensor, if we take one of these sides, 24 millimeters, and we compare it to the actual size of a 30 millimeter camera, so here, let's see, I meant 35 millimeter camera, if that's not what I said. We see the width of this sensor on a 35 millimeter camera is 36 millimeters. Now we can look at this crop sensor. We find out that it's 24 millimeters. So if you simply take, now the, let's see, open up a calculator here. If you take the size of the 35 millimeter frame, 36 millimeters, divide it by the width of the smaller frame, you find out exactly the multiplication factor, or just how much smaller that particular sensor is. So the crop sensor is 1.5 times smaller. That means that if I am using a 50 millimeter lens on the crop sensor, it's as if I'm using a 75 millimeter lens on the 35 millimeter camera. Now similarly, we can figure out the same thing with this Panasonic camera. So we again take 36 millimeters, the size of the full frame sensor. We find out the width of the Panasonic lens, and let's see, I said it was a, it's not on this particular one, so I said it was 7 millimeters in this case. So I'll take 36 millimeters, divide it by 7 millimeters. We find out that it's about 5 times smaller. So it's 5 times smaller than the 35 millimeter camera. So then all I have to do is very simply multiply that focal length range that's on the front by about 5. So 6 times 5 is going to be about 30. 72 times 5, it's going to be about 420 or so. So you will see that, that I was more precise when I did the calculation before, but this is how you can figure out the equivalency, and you can normalize this information from one camera to another, which can be very, very useful. Okay, let's take a quick 5-minute break, and when we come back, we will continue talking about digital cameras.